Thanks, the organizer, for give me the chance to present the work that we are actually submitted. Is under revision. It will be soon on our archive. This is made in collaboration with this bunch of people, but this just follow a long tail of papers where also Anna Romanowski and Francesco collaborated. So I'm going to talk about this quantity, and this is going to be the outline of my talk. So this is a very simple quantity. The dark matter fraction tells us how much dark matter is inside an FT radius with respect to the total mass. It's a fairly simple quantity that actually carries a lot of interesting information on the assembly of galaxies, and in particular, I mean, maybe we cannot learn much about the formation of galaxy, but it's definitely a quantity that you want to compare to the different evolution scenario. So you can have a little algebra and figure out that this quantity is correlated to the total mass that you can measure as long as you have a spectrograph by measuring the velocity, so the kinematics of the central part of a galaxy, or if you go further, you can also measure the kinematics of discrete tracers in galaxies, and or if you have a space telescope, you can also observe a strong lensing, and in both cases you can have inference on the total mass. For the stellar mass, is a little bit more complicated because I mean there are different issues in stellar population that might affect your conclusion. In particular, the problem with the IMF, which we know is the largest uncertainty on our stellar mass inference. We can probably solve the problem using gravity-sensitive lines, but this costs a lot. We can also have constraints from the dynamical models if we look for the best compromise, the best mix of stellar mass and dark matter in the central galaxies, and both things tell us, I mean, can actually help in measuring the stellar mass. The problem is that this problem with the IMF again comes out because we have to at some stage we have to make some assumption, and we don't know exactly what a real IMF in galaxy is. And so if this parameter here, which have been already heard about it somehow tell us about our ignorance on the central on the IMF galaxies, and this can give big biases in our estimates, because this quantity, if we assume a wrong IMF, we can have a mass to large ratio estimate, which can be two or three times larger than different from what we have assumed. So this affects our conclusion on dark matter, and we will see what's the problem. We will see how this works on the real data, and definitely then we have also the problem of dependence of these quantities from the sigma, stellar mass, density, and these also relate, as well as the dark matter fraction seems to be correlated to the same quantity. So there are a lot of somehow a lot of degeneracy that we have to solve to have final conclusion on these quantities. And furthermore, to make things more complicated, we don't know much of how much this quantity changed with the redshift, and this is going to be mainly the matter of this talk. Just before I ran out of time, these are the results that we obtained with our data, and we see this is the dark matter fraction in one of the version that I told you about. And what we are actually measuring is that this quantity seems to decrease with redshift. So the larger, the further the galaxy are, the less dark matter fraction they have in their center. And let's see how this comes out. So again, this is a simple quantity, but is the reflection of very complicated situation in the center of galaxy. These are simulation was just mentioned before, Woodall 2014 is a dynamical simulation. You see here distribution, the density distribution of dark matter and star in the center of galaxy is 1 FT radius. So you see that the situation in the center, once you have you fully account for the baryon physics, it's quite complicated. The dark halo are not cuspy halo anymore. They tend to have even a peak, a more peaked profile, which means that there's some again baryon physics affecting their central distribution. There is a variety of velocity dispersion that this distribution of mass produced in galaxies. You see here is the one in the FT radius, and also a variety of anisotropy. All these things have to be taken into account when you do your models to infer the dark matter in the center. Fortunately, I mean, this can help. We have some prediction of the dark matter fraction in the center of in the center of galaxy here in the FT radius, and it seems that these are correlating with the FT radius, and this is something that we have actually observing also in the data here. So. So central galaxies are important, and we saw that we've been hearing a lot about this during this conference. Is important because there is also there are scaling relation which are changing with redshift, and in particular the size of galaxies changing with redshift. So they're very they are the region of galaxy which are very affected by the formation processes. And these are definitely interesting regions where to look at how the dark matter also changes. So not only the light, but also dark matter change. And we see here that for instance, the change of the FT radius with redshift obtained with data from Werther's company in 2012 is just one of the many results that show the size evolution of the galaxy. So. We want to check whether this evolution in the center of galaxy we know there is in light is also present in dark matter. What we know about redshift 0 is about this is a very brief and limited summary, but we are here different inference from different probes. Here is fiber spectroscopy, this is integral field spectroscopy, and this is lensing, and all results mainly converge on the fact that the dark matter fraction have to change with mass, and they seem to have this minimum around this magic number that we heard about. Is stellar mass of 10.5 index. And this is what we got from dynamics. This is results from lensing from, for instance, Ojo et al. 2010. And we see how different the results change if you change your assumption on the IMF. So if you assume a heavy IMF like salpeter, the dark matter fraction below are lower because, of course, we are assuming there is more stars. There's a larger amount of stars in your galaxies. If you assume a shabby IMF, the dark matter fraction increase because you're putting less star into your center, and so that, you interpret the lack of stars into a larger fraction of dark matter. And you see the big difference. So it's very important to have this to take this into account. And an interesting thing here I wanted to point out is that this shape of the dark matter fraction, this minimum around this mass, has to have something with what we heard about the abundance matching results, because this is the scale more or less where you have the maximum of star formation efficiency in the halos. Although I mean we are looking at the center part, it seems there is this connection, and in fact we put the stellar mass versus the dynamical mass in the center, we have something like that, but we know that the dynamical mass in the center is just a little part of the full of the global mass, the total mass of in a dark halo. So if we multiply this by 20, the dynamical mass, we obtain this. If we multiply by 100, we see that the correlation between stellar mass and total mass is just overlap perfectly with the redshift equals zero equals 0 of the Conroy et al. Wechsler 2009, for instance. So there should be a connection between these results, the results in the center, and the results on the global scale of of the dark matter halos, which is kind of interesting. Of course, I mean, what you once have not to be, we have not to be very, we have to be very careful when you use this conversion, because, for instance, in this case for capillary, this can change, so that means that if you go to this scale, there should be the dark matter fraction actually has to be has to grow slowly than what is done by this correlation. And the only inference we have for dwarf galaxy, for instance, I know about is this one that we had in the Virgo dwarf galaxies, where we obtained the dark matter fraction. If we put this number on this plot, it goes exactly here. So again, I mean, it seems that this connection between the central part and the global part in a dark matter halo are almost at all scales. Okay, okay. Then we have the problem with the IMF universal. So dark matter fraction change with mass, but also IMF change with mass. So it means that probably, what about if what we are looking, what we are seeing is just an effect of the IMF change? If the IMF, so here we have the results of on the variation of IMF, which can be measured by this IMF mismatch parameters defined in different way, where we see that and this different work, different project data all show that this IMF can change with this velocity dispersion, or even the stellar mass here in this case. So it means that more massive galaxies have a heavier normalization IMF, while lower mass have a lower normalization. And in principle, this so in some sense, if this is the case, so if all the variation that we are seeing in the mass discrepancy in central galaxy can be just interpreted in terms of variation of the IMF, then all the scenario of the dark matter fraction. So the dark matter fraction should just be a constant quantity along these lines. So this is what we have redshift 0. We want to then go to higher redshift, and we use here this telescope, the VST telescope. To this a telescope, a 2.5 meter telescope, field of view 1 square field of view, and with this pixel scale. So we are this also called very small telescope for these sites. But we are with this telescope, we are actually observing what area of the sky with the kids within this kids survey. And this a survey which have been already heard about is a deep survey covering 1500 square degree of the sky, and there it is 2.5 deeper than SDSS. So this is mainly conceived for gravitational lensing, but this image quality is perfect also for galaxy evolution. And these are some images that show you how good is the quality of the data that we can have with respect to SDSS, this SDSS. So we can actually use this data to have a very nice and precise and accurate a measurement of the light distribution within galaxy. So we can model perfectly the center of a faraway galaxy up to redshift 0.7, as can I show you. And the quality is so good that you can also find strong lensing in this galaxy. So this is the status of the survey. I don't want to go into the many details. So this is most importantly is the coverage. This is the Kids North patch and the spectroscopic coverage of the area. So we have both data which are of the resolution good enough to make central kinematics of our galaxy and then measure dark matter fraction. So, and we have collected we have collected galaxy in this mass range, in this redshift range, so we can we could measure the velocity, the dark matter fraction in this parameter space. We actually, so in particular, we collected about 400,000 galaxy with the quality, with the image quality good enough to measure structure parameters of size, Cersei index, and as a function of redshift, and only but only 4,000 of these galaxies have also spectroscopic coverage. So this is going to be the sample. I'm going to show results in a moment. use gene sequestration to derive the total mass inside the FFT radius, and also infer also, and in the same time also infer the IMF variation. This is a technique that we have tested at redshift 0 on a sample of galaxy. We had also surround data, so we are pretty confident that our analysis, despite using just a fiber spectroscopy, is pretty much accurate. And these are the results. So these are the dark matter scaling relation for redshift 0, the purple line, and redshift, so for redshift between 0 and 0.3, the purple line, and redshift 0.3, between 0.3 and 0.7, the red line. And you see that for most of the scaling relation, this dark matter fraction versus FFT radius, Cersei index, that's velocity dispersion, stellar mass, and so on. And you see that most of the scaling relation change going from low redshift to higher redshift. So there is some evolution. But if you just wrap up all these results and you put in a plot I showed you before, then you see that the dark matter fraction definitely changed with the redshift here. So there is a decrease of redshift. If you do the same, if you want to estimate the IMF discrepancy, then we find the same this kind of correlation with the same quantities. And you see that the IMF again has to change with in our sample as long as we go toward say more massive systems or larger systems, so more massive galaxy. The point is that this area here is somehow disfavored by stellar population models. So that seems to be a tension between the delta IMF that we measure in galaxies if you assume a dark matter fraction equal to 0. Okay. Then if you change the dark matter fraction in the center of your galaxy, then the delta EMF, so the quantity of mass that you have to put in your stars decreases, and then you can solve partially this tension here. So that means that a constant dark matter fraction equal to 0 doesn't really fit. I mean, it's not consistent with our data, but we need some variation of the dark matter fraction, especially for larger galaxies here, to solve this problem. So now then, okay, so dark matter fraction has to change. Now we want to see how this fits into an evolution with redshift. So to see whether this can be understood in terms of assembly of galaxy, we use first we check the regenerative bias, and the results don't change too much. But then we checked the prediction that you might expect if you put it in your some puffing up models in your gene sequestration. Then you can assume that the FFT radius variation, the evolution of the FFT radius, the size with redshift, and you put in your gene sequestration. These are the prediction of the variation of the dependence of the sigma with FFT radius in these models, and you see that you find something like that for these fundamental models, which don't reproduce the decrease of the dark matter fraction with redshift. Okay, so these seem not to work well. While merging model from Hopkins et al., which are more complicated model dependence of the dispersion with the evolution of the sites, do a much better job. Oops, where is it? You can probably, oh, you cannot see here, sorry. So they do a much better job. It's actually, I think they're missing here. So they go much better through the results. So that seems emerging works much better than puffing up model. Unfortunately, emerging don't work for the IMF variation. The problem with merging, if the merging is the mechanism of producing the variation of the dark matter fraction, then it doesn't work for the IMF. So conversely, it doesn't work for the IMF. So because merging, generally, if you add smaller mass galaxy during your merging, they carry on a lighter IMF. So they tend to have, so going from the past to the present, they should have a flatter or even decreasing IMF variation rather than an increasing, because you add up low mass IMF galaxy here, you add up, and then you dilute the IMF for bigger galaxies. So this trend cannot be understood in terms of merging. So it seems that then the merging play an important role in dark matter fraction. Okay, this is what I just said. So if you wanna just in the last minute, I would like to go a little bit more into the details of how we can interpret now the size, all the scaling relation variation. And I'm using here these models from Ilse et al. 2013, where they have shown how major merging produce the size variation in galaxy of during the growth in mass here. In case of major merging and minor merging. So major merging produce a much smaller size variation with respect to the minor merging, where the growth is much steeper. And the same thing happens to the dark matter fractions. So if you use these models, is what just said, if you use this model, we can now reproduce how the size mass as a function of redshift we are measuring in our galaxy can be explained. So this is the size mass for high mass high redshift galaxies, intermediate redshift galaxies, and low mass redshift galaxies. So galaxy evolved from this bin to evolve from these bins to this bin along some evolutionary track, right? So if we take a galaxy of 11.4 mass here, and we use the models from Ilse et al., we see that for major merging, they grow their size along this line. So they don't jump from this part of the plots to these ones. So in major merging, they don't have the power to make the galaxy grow in size as expected, as seen here. So while minor merging, we see in this side, here do. And we see that this is the track of minor mergers that can allow after 2, 3, or 4 minor mergers, this is 20% mass added, to move from this part of the plot to that one. So, and the same is also seen in the dark matter fraction. So this minor merger allow to make the galaxy to move along this track and then evolve. Of course, I mean, this can change slightly if you change the recipe of your virial mass and stellar mass growth. You can pick what is the best model for you. But generally, in principle, what it seems to be the best model to interpret our results, it seems that the adiabatic contraction, the merging with adiabatic contraction, is the one that better reproduce the steepness of this growth of our galaxy in this plot. Okay, so take-home messages. Sorry for running a little bit late. So definitely, it's important to have a larger spectroscopic survey, because also with limited kinematic information, because these can produce large samples that allow you to explore in the best way the parameter space and have different projection in the scaling relation, both for the light and the dark matter. So the dark matter scaling relation had to be interpreted together with the luminous matter scaling relation, and together have to reproduce the expectation from your evolutionary scenario. We have seen that the results from Kitts plus Boss redshift is lower than 0.5 are mainly explained in terms of a minor merger scenario. This is not surprising in some sense, because we know that in these mass ranges are the major mechanism to make galaxy grow. But it's good to see it and to check against not only the light scaling relation, but also the dark matter scaling relation. And finished. Yeah. No. Yeah. A gas-rich minor merger. Gas-rich minor merger would produce would bring more gas probably into your system, and then sink into the center. Probably have no. But this, I mean, if minor merger, I mean, that's not really changing a lot the quantity of your stars inside, because these minor mergers are really minor. So it's that if you want to produce a growing of the size of the galaxy, you definitely have probably to include minor more dry mergers, because wet mergers will just bring gas that which sinks into the center and probably gives you at the end some more compact size, right? So generally, when we talk about these merging events in the late epochs, they are definitely dry, more dry, right? But I mean, even if you have some minor, some wet mergers, they should just bring a little of extra stars that don't really affect it's just probably a few percent. It don't change that much. It's more important what they do for the site's evolution rather than the mass that they bring inside, I think.
Okay, let's thank Nicola one more time. So our next speaker will be Raymond Simons, who will be talking about kinematic